Hi folks, so I found this paper from the recently concluded Splash conference. It used to be called OOPSLA, that's the main conference for programming languages, compilers, that sort of stuff. And this takes a really interesting approach to how to write programs that have some sort of AI and LLM integration in them. They call it meaning typed programming, and they have implemented this in a language that is a superset of Python, but should look familiar if you are a Python programmer. Let's first try to understand the problem they're trying to solve exactly. Now, if you want to invoke an LLM in your code to handle some kind of logic, some kind of natural language, understanding task, classification, whatever it is, the way you typically do it in code today is that you have some kind of a prompt that you've manually crafted, maybe in a different system, and that's the prompt you will send into some sort of an API that calls an LLM with that prompt. You'll typically also splice in some values you've gotten at runtime, like reading in some data or the user's input. And then when the LLM returns a response, you'll have some code for handling the output and parsing it and putting it into some sort of a structure or a type that you were expecting back. The goal of the authors in this paper with meaning typed programming is to abstract out all this manual work of integrating your code with an LLM. So let's look at how exactly they do that. The running example they use in this paper is of implementing a video game and wanting to write out the logic for creating the next level in a video game given the previous level. And they have some structs that define your state in the game and how a level is defined and so on, but that is their running example. And this is how you would implement this with your regular LLM calls in Python. Let's just assume the running example they're taking is that you want to use an LLM to generate the next level. And this kind of code should be pretty familiar to anyone who's been calling LLMs from code. You'll typically have a prompt. The prompt is going to have some variables in it which will get populated with runtime values, in this case the previous level. It's going to have some description of the problem or rules for how to solve this problem, in this case how to generate the next level, and then you'll also describe what output format you want. You're going to then call the LLM, and then there's a ton of code over here to take the response from the LLM and parse it into a level struct, what you'd expect. And what they haven't shown over here is that you also have to deal with errors, because sometimes you might get parse errors and then you have to handle retries and so on. So this is a lot of manual work. This is the kind of thing that the authors want to fix. Let's look at how the code would look like in their new language, and then take a look at how it works internally. So in this new language, they call it Jack. It's a superset of Python. They have a new language keyword. They call it by. So you define your LLM. In this case, it's GPT-4o. You define your function signature. So note all the type hints, both for the inputs as well as the outputs. And here's an interesting new thing. The keyword by followed by an LLM reference at runtime. And that's pretty much all you need. So they have abstracted away all the prompting and calling of the LLM and parsing the return value. Now you might say, well, this looks very short. How are they getting all that information, the information required to actually understand what get next level should do, all the information that was in the prompt that we saw in the verbose example? And this brings us to the key idea of this paper, which is that if you just look at the way the signature is written, the way the types are defined, because note that this level type is defined over here with all these fields, and the fields have more or less descriptive names. So that's the assumption that this entire scheme turns on, that we write our programs to be readable by other developers. We give them descriptive names, both for types as well as methods and functions. And now, today, using LLMs, you can actually understand those semantics and use that semantic understanding to then craft a prompt to use, to give to the LLM to implement some kind of functionality. And here are a few other examples where they give a little code snippet and what its meaning might be given just the strings in that code snippet. Now, internally, the way they implement this is very much like a regular compiler, except that this compiler is now also tracking semantic information that it's using to construct a prompt. As I say over here, when they get to a place where you're using this new by keyword statically at compile time, they extract the semantics of the code around that call site. And these semantics are what help you generate the LLM prompt. And there's a lot of relevant information to go on. Of course, you have the types and the function signatures and the source code around it as well. And once you have this, you lower that to what they call a meaning typed IR, intermediate representation, that captures all this information. This diagram explains how the system works end to end. So this is a source file, and you have this by LLM keyword over here. Another important notion is this semantic registry, which contains semantic information throughout the code base. And what this really lets you do is look at all the references of the thing that you're trying to use an LLM for. So in this example, it's referring to a type called level. And so you're going to look up level in your semantic registry. And level might be referring to other types as well. So you're going to do this recursive lookup because all these referenced types are going to have a lot of rich semantic information to go on. And using all this semantic information, you're going to come up with a prompt, which is something like this. Now here the prompt is pretty generic. This is what's baked into their runtime. So this prompt is going to get used at runtime. It's going to populate values that are known at runtime, in this example, the previous level. And all this semantic information about what the types mean is coming from the semantic registry that the compiler built at compile time. And the runtime, this new runtime that they've built for this language, is what is gonna make the calls to the LLM, get the response, do all that output conversion. And if it fails, it's gonna do some kind of retries and back off and so on. So it's abstracting away a lot of that common low-level logic you have to use whenever you interact with an LLM. So in terms of evaluation and looking at how some comparable systems behave, they looked at LMQL, which is another system that lets you do LLM integrated programming. However, that still isn't abstracting away a lot of the details of the prompt. And then the other big one is DSPy. As they point out over here, in DSPy, you still have to write a lot of DSPy specific code. And a lot of this semantic information is hard for DSPy to get at without parsing the entire code base. And you can see that in some of these comparisons over here. You can see how long the LMQL code is and how long the DSPy code is versus the meaning typed programming code over here. Now, actually, to be fair, this meaning typed code snippet over here is much shorter than it actually is because they're not including the lines of code for the definition of level, which goes in as this base model pydantic class over here. But even if you count that in, it would still be shorter than the DSPy version. They actually also went and evaluated these three different systems with some programmers, and MTP, meaning type programming, came out ahead on all these dimensions, like how hard the learning curve was, how easy it was to solve a problem, how easy it was to use. And that's not really surprising because so much of the messy nitty-gritties of interacting with an LLM have just been abstracted away. And all you have to say is by LLM, use this new keyword they have. Now, one question you might have is, well, all this really depends a lot on my naming, how well I've named my types and methods and so on. And they actually studied how much degradation they get if they use bad naming. And so this is really interesting. So they have original code with nice descriptive names, and then they steadily degrade it. They have short names, they have a quarter bad names, half bad names, and you can see when you have a quarter bad names or half bad names in your source code, the degradation is very small. It's still in the high 90s. And then if you go all the way up to 75% bad names, that's when it really falls off a cliff. So it's good to know that there's some resilience built in there. I think this basically is saying that LLMs are now good enough that even with bad naming, they are able to extract semantic intent from code, or at least from types and names and function signatures. All right, so that was a quick look at meaning type programming. I thought that was a really nice, clean abstraction for how to write code that interacts with LLMs. So it would be interesting to see more such things integrated into the language level, into the runtime. I wonder if Python will ever get something like this, the official Python language. Now, one question that is still not clear in my mind, and if any of the authors happen to watch this, I'd love a comment explaining it, is why you need a full new language and runtime to do this with. Now, they might have other research goals with the Jack language, and that's fine. But at least for what's described in this paper, I think you could do all of this with a decoration and the runtime reflection that Python already has. So I'm not sure if I'm missing something, but I think you could do all of this without creating a new language. Anyway, I hope you enjoyed that. If you like content like this, consider subscribing, like the video, and I will see you next time. Thanks.